and the clicker is working. Okay, right. So quick structure. I'm going to give a quick intro to myself and the topic. There will be main presentation consists of 3 parts, which is infrastructure monitoring, which I'll only talk about high level, won't be getting into any details, and then code monitoring, machine learning, monitoring machine learning components, and summary along with some suggestions on what you can do to improve your monitoring. So, okay, a little bit about my background. So my educational background is all in physics. Yes, I'm one of those kind of data scientists by trade, by physicist by degree. So I got my bachelor's at Moscow State University and my master's at the University of Alberta. Right after that, I worked for a small aerospace startup, did a little bit of data analysis and image processing. Then I worked on building machine learning components inside the Splunk ecosystem. Some of you might have worked with the product. It's about doing machine learning analysis on log data mainly. And currently, I'm a data scientist at a company that did not wish to particularly be named. And so for those who are interested, you can check out my LinkedIn profile, and it's all there. And I'm also an organizer at meetups, PyData Montreal, where we invite presenters to talk about different concepts that surround Python, data science, etc. Okay, these are a couple of nice pictures from the very first company that I worked at. This is the camera installed on board of the ISS, and this is a picture of Kiev that was acquired by one of the satellites owned by the company. This is a screenshot of the machine learning toolkit that was part of the team kind of working on it at Splunk. Okay, now let's talk quickly about what the sort of general life cycle of a application, and specifically machine learning applications. So you start with business requirements, something that you need to solve a particular need for the business. Then in case of machine learning applications, there's usually some data involved, so you spend some time collecting it, cleaning it, and then you sort of enter the stage where I would say like it's a sort of a Kaggle stage of the process where you train and iterate on your model, try to get the best performance possible. And then you go on to implement all the kind of non-machine learning related code that could be a REST API and things like that. So basically getting the input data, feeding it, like transforming it, feeding into your machine learning model, and then serving it in some way. Then you get to the deployment stage, and then you start monitoring your system. And monitoring is not kind of like you're not done at this point, because whatever you monitor, it will later feed into previous stages of that life cycle. Like a couple of examples would be, let's say that you see that your prediction and times that it takes to serve a prediction kind of above the level that you need, that you expect, then maybe you need to scale your machines, have more machines serving kind of the same model, or maybe you have some edge cases that you did not think of during the implementation, so you go back and change your implementation, or in some cases you might see that your model actually does not give the right predictions. Then you go back to the training stage of this life cycle. Okay, so why do we need monitoring? It's sort of like an obvious question, but what happens when you have no monitoring? No monitoring turns into end-user monitoring, which in some cases turns into Twitter monitoring. And if you go on Twitter and just search for website is down, you'll have like a wall of different tweets. And I like this particular one because on March 31st this year, there was a World Backup Day, and the website of worldbackup.com was down, which is kind of ironic. So don't do that. Okay, what are the sort of general layers of your application? So you have, in case of machine learning applications, you have some, at the core, some machine learning component. It could be a model. And then you have some other code surrounding it. And all of that runs on some kind of hardware infrastructure, or like cloud infrastructure, for example. So, and now we go on to different types of monitoring. So the first one is infrastructure monitoring, where you monitor your CPU consumption, your storage, your network security, and things like that. I'm not going to be going into like details of this part. It's important, but I think it's a bit less relevant to the idea of this conference. But some of the common tools for infrastructure monitoring is Zabbix, Nagios, and if you're running on AWS, that would be Amazon CloudWatch. Okay, let's talk about code monitoring. So in my mind, it's generally can be split into like two parts, where you have instrumentation and metrics. And some of the common tools used for that is StatsD and Prometheus. I will be talking about a bit more details in later slides. And the second part is event logging and tracing. And some of the tools is Logstash and Splunk, the product that I used to work on. And what are the main differences between them? So instrumentation and metrics, it sort of gives you the overall view of how your application is performing. Usually we're talking about time series metrics, aggregate metrics, some kind of averages or 95 percentiles over time and things like that. Event monitoring is something that you need when you need to investigate the path, a particular path that your software took during a particular event. So if, let's say, if you're running an e-commerce store and most of your users are able to make purchases without any problems, but you have a small percentage of users that fill their cart but cannot do a checkout, then you want to investigate like what is shared among those users to kind of fix your implementation. And now let's talk about StatsD. So this is kind of the simplest case of putting instrumentation within your application. And it's very lightweight and simple to use. The general kind of structure of it is that you have an API client within your application which collects the metrics that you're interested in. It batches them up and sends them in batches through a UDP protocol to a collection backend, which usually is some kind of separate server or a collection of servers. And the reason it's lightweight, simple, and non-blocking is exactly the UDP protocol here, which some of you who are like know the differences between UDP and TCP protocol. Like in case of UDP, like you don't get the confirmation that the message you sent was received, but at the same time, this is like for this particular case, when we're talking about aggregate metrics, that's actually a good thing. Like if you lose 1 or 2 packets, that's not the end of the world when you're dealing with millions, but your averages and aggregate metrics don't really change. And the types of metrics that you can collect with StatsD is counters, if you need to counter certain types of events, timers, how long a certain event took, gauges, which is something that you can set at a certain level and it will be maintained at this level throughout time unless you explicitly change it, and sets, when you need to see or count the unique number of items in a particular list or array. It could be the unique number of users on your website and things like that. And it uses external storage, as I mentioned before. It sends its metrics through UDP protocol somewhere else. Okay. And this is the general structure. Like in this case, let's say if we're talking about some kind of application, in this case it runs on Node. So you have an application. Within the application, you have an API client that sends UDP information to daemon that collects them and then later sends them in batches to a backend. Okay, now let's talk about Prometheus. It's very similar and very different from StatsD at the same time. It has similar functionality and a bit more, but it also a bit more kind of less lightweight, I would say, because it has built-in time series database, it has visualization dashboard, and it uses local storage for storing its metrics. And it also has its own query language called PromQL. So don't be confused. It's not based on SQL language, so it's very different. The authors claim that it's optimized to query time series data, and it has some basic alerting functionality. And the reason I have a star near local storage, I just wanted to highlight and kind of make a mental note to myself that this is a very kind of deliberate decision to keep it this way. because you can spin up this instrumentation without any kind of external surrounding infrastructure. And it has both positive and negative things, like from the positive side, like because you don't need to do all the extra work. On the negative side, if you have lots of metrics and you can fill up your local storage quickly, then it's a problem because obviously you need storage to run your application. And this is kind of the general workflow and architecture of Prometheus, where you have targets, things from which you collect your data. And there are two different groups of targets, things that push data to Prometheus because they have specific, like Prometheus has exporters for this type of things. And then you have targets that you need to pull metrics from. And then there's a service discovery thing where you can, based on where you run your application, it can detect that it's running, like let's say on Kubernetes, and it can start collecting crucial metrics from kind of that service. And then you have alert managers and some visualization front end. In this case, it's Grafana. Okay, a bit of kind of snippets of code on how you would use one or the other. Like, let's say you have a Python application, there's like some imports, and then you can create a counter. And in this case, here you will have your external server, and you send your UDP packets to this port. And let's say after that, you have your main application code. And in this example, let's say if you wanted to count how many users had problems accessing your homepage, so they got a 400 error. So you just, this is sort of what the only thing that you need to do pretty much. And you see that the data model that statsd support is dimensional, so you can start with HTTP requests total, and then instead of home, it could be other types of pages. And then you can query depending on kind of, or do a group by depending on this value. And then instead of 400, it could be different types of error. But kind of, you get the idea. Very similar structure for Prometheus. You import a counter, you create it in a slightly different way, and then you kind of increment the number of that counter. Some of the differences, kind of rule of thumb, is if you just starting out with instrumentation and metrics, and you want simplicity and low overhead, you would probably start with statsd. On the other hand, if you have kind of more mature application and you run it on multiple services and maybe containers that are dynamic, and you kind of spin up more or less of them depending on your load and things like that, you'd probably want to go with Prometheus. On the other hand, if you already have statsd and you want to transition over to Prometheus, they have a statsd exporter. What allows you to do is kind of, you don't really need to change your application code that has all these statsd metrics implemented in it. What you do is you just send them to a different backend, which is a Prometheus backend. And then over time, you can kind of change your internal code and move entirely to Prometheus. And for visualization, there's tons of options. They all pretty much do the same thing, but the most common one, as far as I know, is Grafana. And that's pretty much what happens. Like, it doesn't matter where you kind of have your metrics implemented, statsd, Prometheus, or something else. That's pretty much what your dashboard will look like. So you have like a bunch of time series. It's very easy to create them because you don't really need to write much code. It's like point and click kind of thing. And yeah, you can create like time series graphs, counters, and some heat maps and histograms and things like that. Okay. The second part of code monitoring is event logging and tracing. And in this particular case, I'm going to be talking about just Elasticstack because it's sort of like the most popular open source tool that's out there for this purpose, but there are many others. So an Elasticstack consists of several independent components, and I want to highlight the idea that it's independent in the sense that they can be used individually, but often they are used together because there's some additional benefits in terms of integration that you get if you use kind of the same tools from the same ecosystem. So we have Logstash and Beats that allow you to collect metrics from different things, like you can collect your logs. Oh, sorry, I misspoke. Not metrics, but in this case, it's particular log events. So it could be just files on disk. It could be like web server logs and things like that. And then for storage, you can use Elasticsearch that will get that data, index it, and then for visualizing the results, you can use Kibana to kind of create dashboards. And the last thing is sort of, this is not a free component. So there's an Elastic company that is the main maintainer of all these tools. And the way they make money is they provide services around all of this, but as well they provide additional features. And Elastic Stack features, which is formerly called XPack, provide some additional features such as security and some machine learning functionality and alerting based on that. And this is your kind of typical pipeline. Let's say if you have just files stored on disk, you collect and transform them using either Logstash or Beats, search and analyze in Elasticsearch, and then finally look at them in Kibana. This is the basic Logstash config. Don't read into this. It's just the kind of main things that consist of inputs, filters, and outputs. So inputs is you point it to where your log data is located. Like in this case, it's on disk in this file. And then in filter, you tell it how to process different types of logs and how to parse them so that if you have a log event in your file, you're probably not interested in every single thing that's in there. Maybe you want to extract some values. That's kind of where you do that. And then once you parsed those logs, you can send them, in this case, to Elasticsearch located on the same machine at this port and print them out to standard output. OK, this is Kibana. Not really much to say here is that once you have your your data in Elasticsearch, you just connect your Kibana to it, and then you can query all the events. And because once you extracted all the actual fields, you can query by certain field values. Like if HTTP code here is like 304, and like the type of event is HTTP request. So that's sort of what you get there. And XPack allows you to kind of plot certain metrics over time, and then maybe create anomaly detection models, and after that create an alert based on the fact that certain metrics are outside of the confidence range of your model. Okay. And let's talk about Elastic Stack and a lot of other proprietary tools. So the fact that the tools themselves are proprietary and you need to pay for them is not a bad thing itself. But something to keep in mind is that like open source versus proprietary, which oftentimes means customization versus kind of off-the-shelf prepared features that work right out of the box. And usually if you work with open source tools, you need a bigger team to maintain and use them. So you either pay developers or you pay the company. OK, and the last part of my presentation is monitoring machine learning components. And kind of the easiest thing to do, and if your particular business case allows for that, is when you have a continuous stream of ground truth, maybe lagging not that far behind your predictions that are made by the machine learning model. And what I mean by that, let's say your machine learning model serves some kind of predictions, and then you get a stream of ground truth a week later. And it could be something where, like, there's one use case where you can predict, if you're like a chain of restaurants, you want to predict how much inventory in terms of like meat, let's say, you need, because it's something that goes bad very fast, and you don't want to buy too much and you don't want to buy too little. So you kind of have that fast feedback loop to your model. But in other cases, let's say if you do credit card fraud detection, a lot of people realize that their credit card has been stolen after weeks or months. So you don't have that fast feedback that, oh, my machine learning model like said that some transaction is OK when it actually was fraudulent. So you don't have that very fast feedback. And the other case is in some business cases, in some problems, you actually, at least for now, where we are at in terms of development and progress in machine learning, you still need to have humans in the loop. Because in some cases, it might be required by law. And the last thing I'll talk about is model decay, how you can tell, well, not definitively, but to a certain degree of confidence that your model, that everything that surrounds your model kind of has changed and you need to retrain it now. Okay, so when it comes to human in the loops, so it often frees engineers from dealing with edge cases, which are usually the hardest, because you can train your model to have, let's say, 95% accuracy or whatever, but those 5% accuracy is where you have a probability that the model spits out probability of 51% that it belongs, let's say, in terms of classification, belongs to a particular class. So that's actually where it's the hardest kind of area to improve your model on, and that's why sometimes it's easier to have actually people monitoring those edge cases. And in some, as I mentioned, some industries it might be critical or mandated by law. And the way kind of companies deal with it, if you're a social media company, you create a content moderation team. For medical professionals, they cannot just use a machine learning model to spit out a diagnosis and let's say like to a patient, like go ahead and use it, because that they will be liable. And in some interesting cases, it could be stylists, and I'm going to be talking about that now. So there's a company in the Bay Area, which I think is really interesting, called Stitch Fix. And the way their business model works is actually pretty simple. So you go on their website, create your profile, and you tell them a little bit of information about your preferences in terms of the style of clothing that you like, the fit, the colors, and etc. And what happens periodically, they send you a box of 5 things. And you have an option to pick 1, 2, or keep all the 5, but whatever you send back, you won't be charged for that. And they use that feedback kind of explicitly in their model. But the way, what happens is, once you have that feedback in the database and you train like this, essentially a recommendation system, whatever comes out of the recommendation system doesn't go directly to the end customer. They have a team of stylists that take into account recommendations from the machine learning model. They take into account information that was provided kind of in free-form text by the users themselves. And they also have a lot of knowledge, and this is the critical part. They have this knowledge about fashion and trends, which is like a very hard problem to solve algorithmically. And they take all that into account and kind of boil down that to just 5 things that they eventually send to the end client. They have a really nice tag blog about machine learning and algorithms. Check it out. It's very interesting to read. And let's talk about model decay. So what is it? I actually don't particularly like the term model decay because it sort of implies that your model changes over time. Well, your model cannot change over time unless you change it explicitly because the weights are static and everything. But what changes is the environment that surrounds the model. You have your macroeconomic factors. Like one of the examples could be, let's say if you work in financial industry and your model, one of the features that would go into your model is credit scores for credit rating for different people. So in this example, the distribution of those credit scores was very different before the 2008 financial crisis and after that. So if you train your model here, at this point in time, and then something important happened, there's no guarantee that you can use the same feature on the same model. So another point is data sources and integration. In many, especially big companies, people who are responsible for the data structure, kind of data engineers, are not the same people who train models and deploy them to production. So if something changes about how you collect the data and how you store it, then it might affect the performance of your model. And one of the kind of simplest examples would be, let's say, if your data engineering team updated some kind of data storage technology to a new version that for some reason decided to store timestamps not in seconds but in milliseconds. So you suddenly got values that are distributed in a very different way. And some of it could be what's responsible for environment change is internal changes. Your policy, how your company changed its strategy, or user experience. And this, one of the simplest examples, again, going back to credit card fraud, the way it works is usually, it's not that one person stole one credit card and they made a purchase. This is not actually that big of a problem. The problem is when people buy kind of stolen credit card information in bulk, and they have bots kind of doing purchases at multiple sites kind of at the same time, and very quickly, and they get that product and then discard the credit card information. So the way bots behave, obviously whoever's programming them tries to emulate the behavior of real people, which is not like entirely possible. But let's say what your company is, if you have an e-commerce store, what your company is optimizing for is the time from the moment the person entered the website and they check out, which is actually the same metrics that some bots might be optimizing for, is that they want to complete the purchase in the shortest time possible. And how do you detect all of that is using statistical tests. There's a lot of them. The most common ones is, so let's say if you have some feature X and you have hundreds of features, but one of them is feature X that's distributed kind of in this blue distribution when you were training, and you have this orange distribution after deployment, and then you started kind of collecting the new distribution. Like, it's hard to say whether it's the same or different distribution. Like, they look sort of the same and sort of different at the same time. So here's kind of, I'm showing you how I generated them, and like I'm telling you in advance, these are two different things. So the training distribution is the normally distributed thing around the mean of 500, and the observed new distribution is actually a combination of two, which is one has a mean of 490 and the other one has a mean of 510. If you just wanted to check if their mean and standard deviation is different or the same, it will be almost identical, so you won't notice any differences if you just look at these numbers. So for example, using students' t-test, which is commonly used for A/B testing, will not give you kind of any meaningful information. So what you might want to look at is population stability index, which is kind of a thing where you have your training and observed data, you split them in buckets. Normally it's 10 to 20 buckets, and then you compute the proportion of the training population in each bucket with respect to the total number of items, and you do the same for observed, and then you compute kind of this thing, which is the difference for every bucket multiplied by the log of the ratio, and you sum them all up. And this is sort of the general rule of thumb. Like, if it's less than this value, then you're sort of okay. If it's within this range, then you need to kind of look at that. And if it exceeds this value, then it's no longer a good feature to use. In this case, let's say I use 10 buckets, and this is sort of like the edges of my bins. This is the number in each bucket for the training data set. For the observed one, this is the ratios, and this is the PSI for every bucket, and this is the total sum, which is, as you can see, significantly less than 0.1. So again, like, this test doesn't really indicate that I need to, like, that something like important happened to that feature, that it changed significantly. So the other thing that you can use is Kolmogorov-Smirnov test. This is kind of a more mathematically rigorous statistical test. And kind of, if we're talking about discrete distributions, what you do is you compute cumulative distribution functions for both training and observed data set. You plot, like in this case, I plotted them up, and what your, like this D thing is the maximum absolute difference between two cumulative distributions. And then depending on the number of instances in two distributions, you can compute the p-value for this statistical test. And let's say in this simulated scenario, we have a variable that, like the mean of feature X, let's say it decreases slowly over time. So we have this time axis, and we have 52 weeks, like a year, and it slowly decreases in its mean over time. If you plot the p-value for Kolmogorov-Smirnov test, here's what you would see in this case, where the p-value is at 1 for the first couple of weeks, and what it tells you is that the value, like, it's very confident that the values from two data sets come from the same distribution. And then at some point, it starts going down rapidly. So at some point, like, you want to draw a threshold that you're less confident that two things come from the same distributions. Let's say we set this threshold at 0.9. So, and basically, like in this particular case, like, you'd be probably around 13 weeks. So you'll have to retrain your model. Like, if this is your point of deployment, you'll have to retrain your model somewhere around here. And other ways to detect it is plot average loss function values over time. Like, in most cases, you'll probably see them increase if your environment changes, that your model will kind of be less sure about the predictions that it makes. Or there are ways where you can compute model uncertainty. It's still an active area of research, but there are things where you can, if you have a classifier, it will not only spit out predictions for each class, but it will spit out some kind of coefficient between 0 and 1 about how sure it is that whatever was provided came from the same distribution as the training set. And finally, kind of my summary. I'm sorry, I might be going a bit over time. So production is an opportunity for learning for you. So you collect the data that you have in production, both predictions and the input data, because this will give you an opportunity to improve your model. And good monitoring is automated monitoring, meaning that you open up like a dashboard or something and you can quickly see like an overall picture, that you don't need to like SSH into individual machine, grab for certain value in your log files and things like that. Because as soon as it starts being kind of manual, you'll stop doing it. And monitoring will evolve alongside of your application, which is something sort of was mentioned in the previous speaker mentioned as well. So and my suggestion is you start simple, but you have something first anyway. So, and by starting simple, you could log 2 files at first from your application, and then you implement some simple metrics like statsd, and you put like basic metrics on the dashboard, and that's it. So pretty much your kind of morning routine will be like you come in the morning, you open up the dashboard, everything looks fine, kind of you're happy and you keep working. At some point in time, like you might want, if you have more services, you might want to start logging not to files, but to some kind of data store, and then implement the very basic threshold alerting functionality, because hopefully by this stage, you will already know that what things you need to be alerted on. Later, you can start, once you have more data, you can train your model to actually, anomaly detection model to alert you when something goes outside of the confidence range. And then eventually, depending on how critical it is to your business, you can start detecting when your model has decayed enough that it's worth retraining. And that would be sort of your last part of your application monitoring system. There's some additional resources that you can read up on. Not all of them directly relate to monitoring, but there are just some good kind of resources where you talk about technical debt in machine learning system, or you can figure out like how good your machine learning is if it's up to Google standard, because this is the paper that was released by Google in 2016, and they talk about kind of the best practices for deploying and monitoring your machine learning system. And that is it. So I chose this slide because last year I went to Niagara Falls. I took this picture on my phone and I really liked it. Okay, and this is my kind of social media account. So if you want to get in touch, and thank you.
Alex, thank you so much for your topic. Any questions? No questions?
That's surprising.
There's a question over there.
First of all, thank you for interesting report. I want to ask a couple of questions. One is related, you spoke about monitoring. I'm interested in the rest of the application. Like, will you suggest any maybe framework technologies, or are they at all important when you're deciding like for this customer or this scenario we will use this tech, or you just isolate it into one container, let's say, with a REST request and don't think about the rest of the application?
Okay, so like your monitoring strategy most likely will depend on your use case. Like let's say if you have a use case where like for whatever reason you know that your data distribution, like your input data distribution will not change because like let's say your data is generated by some kind of like machine or some kind of system that doesn't change over time much. So this will affect that. Another thing is if you sort of want to monitor your containers, let's say that you have a large number of them, then you would probably want to use something like Prometheus, which already has a lot of functionality and support built into it to monitor like Docker containers and Kubernetes orchestration and things like that. I don't know if I answered the question.
Yes, yes, thank you. And another question would be, can you trust your production data? Like if you deploy the new model, because not in, you can test very well, but in the production you may have you always have a different data than in the tests. So do you have any differentiation between trusted users and not trusted users, and in order to compare that new model against trusted users, for example, the bank fraud or credit card fraud example?
Oh yeah, that's actually an interesting question. I personally have not dealt with the use case where like you have sort of aggregate data, but it might be sort of subdivided into like trusted and untrusted data sets. Like that would be an interesting case. But what I know that a lot of people who actually deal with credit card fraud, and that's pretty much every single e-commerce store, what they do is they actually allow for a certain percentage of fraud cases to sort of pass. Well, not pass, it's not that they ship the product to someone who didn't really pay for it, but in the sense that they don't train the model on some instances of it. And the reason for it is it's type of case where you have a feedback loop, right? If you train the model and it will only learn how to detect fraud cases that were occurred in the past. And obviously your fraudsters, they change their behavior over time. So you kind of, this might be the case where you want to have people involved there, and they will check certain transactions. Maybe instead of blocking a transaction and saying like, no, you cannot make a purchase, what happens, like, and a lot of companies do that, they actually say like, okay, like we're almost done, but let our representative reach out to you and confirm your identity. When the model is not 100% sure, so someone from your company calls them up, they ask for their ID and things like that, and then once they confirm it, then the product actually gets shipped to the customer.
Thank you.
Hi, thank you for your speech. I have a question about where you saves your business metrics, in which data store? Or maybe you can say where you want to store your business metrics.
Okay, so if we're talking about business metrics, that's usually a data store somewhere where like a lot of what business intelligence like BI analysts would use, right? So from Tableau and whatever. So it might be like things like BigQuery on Google. It could be your Spark cluster, whatever, like anything that your kind of BI software can connect to. But if we're talking about like just data that sort of went into the model and the prediction that was made, like it could be like a separate database sort of where you occasionally output results to. Because another thing sort of to keep in mind, if you have lots and lots of data coming in, you might want to sample it. Like you probably don't want to store every single prediction that was made. Again, it depends sort of on your use case. But if you sample it and you still end up with like millions of values in a week, that might be good enough.
Thank you.
Yeah.
Hello. Thanks for the talk. My question is, do you monitor somehow adversarial attacks on the model that tries to fool and predict the different output? Do you monitor them somehow?
No, and I personally don't have any experience doing that. I probably haven't worked with the use cases where there's like someone actively tries to fool your machine learning model, like other than like credit card kind of fraud use cases. But if we're talking about, let's say, if you have a social media website and you try to block particular kinds of images, and someone tries to train like an adversarial model to produce images that kind of bypass that system, like no, I have not dealt with that.
So thank you, Alex, for your topic.
Okay, thank you.
There's one more question.
No, one more.
One more?
Okay.
Could you?
The last. Okay.
Yeah, thank you for vast overview of monitoring everything. At the unnamed company, how large is data scientist or research organization, and like what is the relation between them and engineers? Do they write production code? How is this thing set up?
Okay, I'm guessing I can share that information. So basically the way the team is structured is we have a data science team, which is about like 8 to 9 people. Like we're actively hiring, by the way, so yeah, keep that in mind. And we have a data engineering team, which is kind of responsible for setting up things like Hive cluster, Kafka Sparks, and things like that. So for them, kind of, they are providing us with all the data, and we're basically just consumers of that data.
And in terms of code, do data scientists write production code?
Yes, so that's one of the things that I really like about kind of the way we're doing things. So we own the project kind of end to end. So typically we have like 1 to 3 people working on the same project, and you start from talking to your, like usually it would be internal clients, you talk to them, you collect their business requirements, and then you start collecting your data, you do research. Like usually you do research prior to collecting your data in order to identify what data you need. Then you do prototyping that hopefully turns into something that you can sort of refactor and deploy into production. And then you will kind of have those cycles over time. If like the first prototype if the clients were happy with the first prototype, then we sort of get more budget and we keep iterating on it.
Like you are really full stack engineering and research and everything in like one team, right?
So we don't do like research in a traditional sense where you do like cutting edge research and then go to a conference like NeurIPS and publish it and talk about it. Like our research is more like of a practical, like applied research where you get a paper that someone already published and they promise like great results, and what you do is like, okay, if there's no implementation on GitHub, then if you really want to try it out, then you go ahead and kind of implement it yourself. If it works, then that's great. If not, then we don't spend much time on it, like we just keep going.
Thank you.
Yeah.
So that's enough, I think. So thank you, Alex, again.
Perfect. Thank you.
Thank you. So it's time for fun now.